Hello, hello. Can you hear me?
Hello,
Yes,
yes, sir, you're audible.
Okay, good. Yeah, you can hear me now, right?
Yes, sir.
Okay, perfect. Yeah. So good. It's good to be back. I have been out of this action for last 4 weeks or so. For some personal reasons, I had to. I could not be taking the classes. So, so how have you been? Have you been enjoying the class? Is there any questions, doubts, complaints, any particular areas that you would like to like to be repeated? um, I mean, before I start the class for today, I mean, it'll be good to know what is the status of this class right now. Hello. No status. So you guys did not understand what the other people taught.
Hi, sir. It's good to see you. Actually, the thing is, some parts we uh, were not covered in that. In that particular time, like some recurrences, like the master methods and these kinds of things. I think we are not covered. So
Okay,
can you just
sure. Yeah, yeah. So in the recurrence, what all things have been done for you guys?
yes, only the basic structure. Guessing the recurrence and then proving it by induction and this kind of
Okay.
things.
Okay, so just the plain guessing the induction, guessing the recurrence and proving by induction. Okay, fine, good. So that is one thing. So maybe I can just share my screen. That will help you guys to see these things. Can you see my screen?
Yes, sir.
Yes,
Yeah. So
sir.
I just want to know what all things have been covered. Okay. So one thing that was kind of covered is recurrence. Yes, so basically, you have been just been told how to prove it by induction, right?
Yes, sir.
This is one thing that has been told to you. Okay, fine.
So
Yeah.
the trivial recurrences like Tn is equal to Tn by 2 or Tn minus 1, not the complex one like Tn is equal to 2t log n like that.
Okay.
The recurrences are not covered.
Okay. So the trivial linear recurrences. I mean, one value recurrences, right?
So, yes.
Yes. So that is one thing that is in one. So the something like t of n equals to 2tn over 2 plus n. Has this been covered? Or something like that?
Yes, sir.
Okay.
Yes, sir.
What about asymptotic notations?
No, sir.
But it has not been properly covered.
It has not been properly covered. Okay, fine. So not properly covered. Okay. Uh, okay. Uh, so then there was another thing on the counting, right? A combinator counting. So what all things have been covered in the counting part? Say balls and beans have been covered.
Yes, sir.
Yes, sir.
Okay. So balls and beans using, I mean, this identical, non-identical, all the settings have been done. So has the
Yes,
table
sir.
was the table
All the
done?
settings.
Hmm? Hello.
Yes, sir. That table was done, sir.
The table was done. Okay. What about generating functions? Counting using generating functions?
Yes, sir. It was done.
Okay. I mean, and you guys are happy with whatever has been done here, right? Or do you want some parts to be explained further or something?
So it would be better if you just go over the Ramanujan's partition functions once more again.
Okay, Ramanujan's partition function. Okay. Yeah, but I mean, I can go over the partition function, but in the partition function, there's not much that I can. I mean, I can just motivate you guys and explain you why this is complicated and how beautiful it is. But in terms of usage of it, at this point, I don't think you have any particular usage of this Ramanujan's partition function. But other than that, the kind of the stuffs like the has something like the Stirling number has been done. Hello.
Yes, sir. But
Yes, sir.
I
Yes,
mean, if the proof is there, it's not. I mean, covered.
Okay, very good. I mean, whenever I ask you, if you should please unmute and shout it out. I mean, there's a huge lag that's coming out from any answers. If only if I'm asking 3 times, are you saying it? That's not very useful. Okay. Okay. Fine. Good. So we are in this situation. Anything else that was covered that I forgot in the middle?
No, sir.
Not as such, right? Okay. So this is how it will happen from now on. Okay. So I will be taking at least one class every week, most likely the Tuesday's class. Okay. And maybe there will be some extra classes that will be taken to make up for some lost classes, as well as, I mean, this particular semester we started 1 week later. So because of that, we have to make up some extra classes. Okay. So on the other hand, there is also the graph theory part. Now, I mean, of course, this graph theory part, you can also ask me if you have any doubts or questions on that part. But from now on, the complete graph theory part will be taught by Devopriya. Okay, so I understand that there is one class in graph theory that has been taken. Okay, and actually Devopriya is a very good teacher, so you should be able to follow. I mean, he should be able to answer your questions and explain stuffs and all very well. But of course, you can ask me anything that you want to ask on in graph theory. Okay, but so every week there will be at least one class on graph theory and at least one class on this particular area. Okay, and using that we will try to go into these various. I mean, this is how we will continue, and there will be some extra classes that we will inform you if when it is coming. Okay. Any questions other than that? Any comments, doubts?
No, sir.
No. Good. So let me start with actually the asymptotic notations. Okay, this might be the. I mean, it's very important for this asymptotic notations to be there. Now, okay. So what does asymptotic notations mean? So there are times when you don't have. So ideally, so if I have a function like this, right? At the end of the day, I would like to say something like, oh, see, t of n equals to some very complicated expression, like maybe it will be n plus log n plus 1 or something like that. A pretty complicated object of this form. Now, this expression is not an easy expression to kind of say, right? Or there are lots of, or if I have things like, say, t of n equals to n by 2 plus n plus 3. Now, this also is a very complicated expression. Why? Because this quantity is not well defined. So this is like, okay, is it the floor of that stuff n over 2 that we take, or the ceiling of the n over 2 that we take, and so on. Okay. So there are many times when we are trying to identify something, some object, some function. Okay, of course, the best thing is to kind of say that this function is exactly this quantity. Okay. So that is possibly the best that one can hope for. But then that has some, issues, right? Might be very hard to understand. It might be very hard to figure out what is important or not. For example, say if I tell you that T of n equals to n to the power 100 log n, n to the power 100 log n plus 5 by log n minus 2 or something like that. Okay, and I have somebody else comes up with another new function, say T2, and say that, oh, this is actually n to the power say 2 to the power 100 log square n. Now, which of these functions are good? Okay, or 2 to the power 100 log square n, say by n cube. Now, which of the functions are which is higher than the other? It's a bit complicated stuff, right? Because the expression here is not as clean as you'd like for it to be compared. So these objects, these things that usually in computer science comes up in time to understand the time complexity or certain properties of some algorithms or something like that. You might have already seen it in your programming courses or something. So the idea is that, okay, I have somebody comes up with an algorithm and somebody comes up with another algorithm, right? So maybe somebody else comes up with another algorithm which says that, oh, see, this is equals to 1000 n to the power 500. Now you want to compare this. So there are three people. The person one has produced an algorithm whose runtime or number of steps that is taking is T1 of n. Person two has produced an algorithm that has the number of steps that it takes is T2 of n. And somebody else, the third person, has come up and given you an algorithm where the number of steps is T3 of n. Now, it is very important for us to understand which is better than what. Okay, and this is where the kind of concept of asymptotic notation kicks in. Don't think of the asymptotic notations as just as some definitions. Okay, there are of course some formal definitions and all, but let's try to understand it as why or what are the ideas behind having the asymptotic definitions like that. So first of all, what do you guys think about, say, comparing this function to this function? Say this function, so T1 of n to T3 of n, which is better?
T3.
T3 is better, why?
Because it's constant into n to the power a constant, and T1 is n to the power constant into log of n.
Okay, you are right, completely right. But
comparing the powers.
But comparing the powers, I mean, so when I asked you which is better, you already assumed something. What did you assume? You assume that, so if you put n equals to 100, in that regime, if n equals to 100, okay, so if say
I
n,
assume that n is large.
exactly, if n equals to 100, then T1 of n is actually much lower than T3 of n. Maybe it is true for even n equals to 1000. Maybe it's also same true for n equals to 10,000. But slowly as n is increasing, okay, so this exponent here has a log n in it. And this log n will just become kind of infinite in some sense, right? It's kind of it can go up to any number. Whereas here, there is this number here that is a constant. So at some point of time, this 100 log n will be more than 500. And in fact, there is also this huge constant in front. But at some point of time, this constant will be overshadowed by the extra that you get from this exponent versus this exponent, right? So in some sense, we are not saying, we don't want to say that T1 is good or T3 is good, but we are only interested in the kind of at very, very, very large n kind of stuff like that. Okay, so first of all, in asymptotic notation, the first thing that we want is that we want to compare functions for large n of n. Meaning as n goes to infinity, what happens in some sense? That is the first thing. Okay. And the second thing is that, like, say, if I am just worried about something like, what about this versus this? What do you think? What about T1 versus T2? Which is better? Which is bigger? Hello? Nobody has any idea what is bigger?
T2 is better.
I think T
You think it is T what?
T2 is smaller, sir.
T2 is smaller. Why?
Take the log.
Take the log. Okay, very good. If you take the log, then what happens?
Sir, its limit tends to 0.
Yeah. Limit n tends to 0. Sorry, limit what? Sorry, I don't get you. I
N
cannot.
tends to infinity, limit n tends to 0. So it approaches to 0.
Which one approaches to 0?
T2.
T2 approaches 0 and then tends to infinity.
Sir, if we take log,
Think about it. Okay, I can give you a very small hint. What is 2 to the power log square n, log n?
Sir, that is n to the power log 2 into log n. And if we do that, I mean changing the base to n in the T2, then we will get the power as 100 log 2 log n minus 3, and which is I mean less than the power of the T1. So I think
Log 2
T1 is
log n.
yes.
What is log 2 are you getting? Okay, so first of all, let's okay, so this is maybe something that I had not specified it very correctly. But usually whenever we think of logs in this world, we think of it to the log base 2. Okay. I mean, this is kind of a standard thing, but again, it will not matter that much. In the exponent, it might matter, but think of it as log base 2, and then what happens?
Sir, sorry to interrupt.
Yeah.
Just I got disconnected, so I wanted to ask that what you have just said.
I just told that in most of CS, in computer science, whenever we say log, you can, most of the time, we mean log base 2. That's all I told.
Yeah, that's fine. Here we are comparing these three, right?
I just want, for now, I just want to look at this T1 versus T2. That's it.
Sir, for T1, it is of the form like roughly n to the power log n, and T2 it is 2 to the power log n.
Why is 2 to the log n?
2 to the power 100 log n square. So that will
Sir,
be less than n to the power log n.
okay. First of all, I think you guys need a bit of a quick brush up of your log. Okay, so let's first of all exponents. Let me first explain. 2 to the power a times b is nothing but 2 to the power a whole to the power b, which is also the same as 2 to the power b whole to the power a. First of all, okay. Secondly, 2 to the power or 2 to the power log or anything to the power, so any constant c to the power log base c of n is actually n. Okay, this is a facts. Okay, these are facts of log and exponents. Okay, the other things, of course, I have not told it, but maybe it's a good idea to tell it to you guys. 2 to the power a plus b is 2 to the power a times 2 to the power b. Okay, I mean, these are high school stuff, so I hope that you can recollect all of them. And now with this information, now look at what is T2 and T1. What is T2? T2 is 2 to the power 100 log square n. Okay, look at this by n cube. Let's think of it a bit later. But this is 2 to the power log square n into 100 log n. And 2 to the power log n is n. I have written it actually right here. Right? So this exponent, what does it end up becoming?
N to the power 100 log n.
N to the power 100 log n. This is same as this exponent. Okay, so we are now talking about this versus this. Okay. Now what happens here? Okay, so somebody in the chat has given the reason why these two are, T1 is bigger than T2 by writing the exponent completely. Okay, and this is a good idea. Okay, fine. Now let me change these things a little bit. Okay, so let me just, instead of here, okay, say here, if I want to remove things like, what do you want to do? Okay, yeah. So say if I did this one as to be, if I just change this thing as instead of 3, I write it as 2, then what happens? Okay, let's see. So somebody, what was the note that you had guys written?
Sir,
Yeah.
in the first question, it should be like whatever in the chat that has been posted. I think there should also be log n multiplied to the both that is in the exponent. Because when we take the log, then whatever in the power that will come in front, and again there will be a log n. So it will also be multiple.
What should be a log n? Can you repeat actually slowly?
Sir, whatever in the chat that is in the left part, that is 100 log n.
Okay, so let's see. Yeah, can we?
Log n.
So it is, I think, what is it? N to the power 100. N to the power 100 log n plus 5 by log n minus 2. Right? So let's see this one. This is equals to n to the power 100 log n into n to the power 5 by log n into n to the power minus 2. I'm using this expression, right? This is equals to n to the power 100 log n. Now, what is this quantity? What is this quantity? This is nothing but 2 to the power log n times 5 by log n, right? I'm using this expression, 2 to the power a to the power b equals to 2 to the power a times b. So that means log n and log n will get cancelled, and this will be 2 to the power 5. And this will be n to the power minus 2. So it will be actually some 2 to the power 5, some quantity, into n to the power 100 log n by n square, which is actually equals to 2 to the power 5 into 2 to the power 100 log square n by n square. And this is exactly same as what this quantity is. Okay, is this clear? This quantity is exactly the same as that quantity.
Yes, sir.
Okay. Okay. So take out from this thing. Okay. First of all, for understanding, you guys need to recap on your this part a lot. Okay. How to play with logarithms and exponents. First of all, it's a simple calculation and all. But this kind of took us away from whatever I was trying to say. Okay. So with this thing, what will happen is that this T1 and T2 are basically same expression away by a constant factor. It's a constant factor away of each other. Okay. And a constant factor away might look bad, no doubt about that. Okay. So if somebody says that, oh, here is my computer that runs at can solve this problem, or whatever problem that it can solve, your algorithm, your computer can will take 10 times more time. It might look bad, no doubt about that. Okay, but it is better than somebody saying that your algorithm, that one computer takes some n times more time than the other computer. Okay, so the constants are something that we have to be a bit careful about. Okay, we are not that worried about constants. So in some sense, we are not too concerned oh god, you know what, I have made a mess of it. My battery of my pencil has died. Just one thing. So anyway, so let me just while I charge my battery, so let me tell you yeah, so in the case of asymptotic notations, we are not too worried about the constants, at least not in the additive constants, and certainly certainly not in the additive constant, and sometimes not even in the multiplicative constant also. Okay, so this is basically where we are. With this, we will go into defining the asymptotic notations. Now, if somebody gives you two functions f and g, okay, and somebody asks you to compute or estimate, sorry, not estimate, compare these two things, what are the things that you would have normally done? Hello?
We can evaluate the functions at different points and then compare the values.
Exactly. So you can evaluate the function at various points and compare the values. And if those values are perfectly matching, so at all the points, if the values are perfectly matching, then you would say that the functions are equal, right? Now, when will I say that f is less than g? Hello?
So the value of f at every point should be less than the corresponding value of g.
Right. So value of the point function at every point should be less than the corresponding value at g. Right, and similarly we can say that f is greater than g, and so on. Right. So let me see. I have my pen has charged a little bit, so I should be able to explain you now. Yeah, can you see me? Hello?
Yes, sir.
Yes, sir.
Yeah. So let's see here. So in the normal setting, if I have to compare f less than or equal to g, right? The standard things are that, okay, I have f is equal to g. What does it mean? That means for all x, f of x equals to g of x, right? And we have something like f is less than or equal to g, meaning for all x, f of x is less than or equal to g of x. And the other one, f is greater than g, that means for all x, f of x is bigger than or equal to g of x. Now the asymptotic notations, first of all, remember that we are not interested in the low terms. We are interested only in the high stuff, right? So I have been given two functions f and g. Both of them you can think of it from the real lines to positive reals to positive reals. Okay, and of course I can also still say f is equals to g, right? Something like we have done, right? That something like here I wrote is equal to. This is an equal to. This is an function. This is the function, and these two functions are equal. Why? Meaning for all point it is same. But maybe there are places where this is not same. Okay. In that case, we would like to say the first thing that one says, the next thing which is slightly weaker than f is equal to g is what is called this f is asymptotically similar to g. What does it mean? It is a limit as n tends to infinity, f of x by g of x equals to 1. Okay, this is the first. I mean, you can see that this is almost as good as this. We're not saying that they're all equal, but we are saying that, okay, only at large enough points they are equal. And they are basically evaluating close to 1. They're basically becoming equal as n increases. So this is called asymptotically similar. Now, have you guys seen this particular expression anywhere?
Yes, sir. I have seen this expression in last assignment.
In the last assignment you have seen. So everybody must have seen it in last assignment. And then why the rest of you are not saying anything?
Like only in the assignment.
Oh, only in the assignment you have seen. Okay.
In the Babai notes it was given.
In the Baba's note it is there. But other than that, I mean, it's okay. So there are two actually examples where it is very much there. Okay. This first is known as the Stirling approximation. This is something that we use a lot in computer science. Okay. So what is Stirling approximation? It says that, okay, so I have this number n factorial, right? How big is this n factorial? Is this n factorial bigger than 2 to the power n? Hello?
Yes, sir.
Yes, sir.
N factorial bigger than 2 to the power n. Okay. How much bigger? Is it bigger than n to the power n?
No.
Is it bigger than some, is it smaller than some particular constant to the power n? Is it smaller than 10 to the power n?
No, sir.
It is not smaller than 10 to the power n?
It will depend on n.
It depends on what?
N.
It depends on n. Okay, of course. Good. So I am just interested in therefore only at the large enough n. Say.
For large n factorial greater than 10 to the power n.
Sorry. Can you repeat? I couldn't hear you. Hello? Whoever told you to repeat. Yeah.
For large n factorial is greater than 10 to the power n.
For large n greater than 10 to the power n. Okay. Is n factorial less than, but I mean, do you have any reason why to believe it or something? Okay, can you say?
Sir, 10 to the power n is basically 10 repeated n times.
Right.
And n factorial is n into n minus 1, and each term is greater than 10. So
other than the first 10 terms, right?
Yes.
Other than the first 10 terms, all of them. Okay, very good. So it is bigger than 10 to the power n. Okay, good. Is it less than some n to the power n? You told it's less than n to the power n, right? You guys? Is it less than n to the power n by something? Or is it more than something? Is it closer to n to the power n? So there are a lot of these kind of questions that are there. Like n factorial doesn't give you a very good sense of how large is it. The Stirling approximation basically says that This is basically, you look at n by the exponent e, not exponent, this e, value e to the power n. Okay, okay, it's not exactly that, it is like this, 2 pi n into this quantity. Okay, so this is not exactly same. N factorial is not exactly same as this quantity, but it is asymptotically similar, meaning as n tends to infinity, this quantity and this quantity matches. Okay. Another way of seeing of a simpler version of this n factorial is that log of n factorial is actually asymptotically similar to n log n. Okay. If you take log of both sides, what will happen? You'll get n, I mean, there will be this term will produce some log, but then the additive part, then this will become n log n minus n log e. Oh, and by the way, I should be very careful. Here, this is e. Okay, so this is a, now in the notes of Babai, you can see a set of exercises that actually goes towards proving this Stirling approximation. Now you can try to solve them, but one important thing to note, and this is something, please memorize almost. This is the one of the few places where I will ask you to memorize something, this expression. Because n factorial is a term that appears in computer science lots and lots. And in many times, you need to have a sense of how large is it. And this basically gives you that sense. Okay. Okay, so there's another place where this asymptotically similar stuff is used. Have you guys, how many of you are from number theory or mathematics there, in fact? How many of you are from mathematics background?
Yes, sir, I am.
You are? You are the only one?
I am.
Okay, so there are a few of you. So in number theory, have you done some elementary number theory?
Yes, sir.
Yes, sir.
So how many prime numbers are there up to number n?
Infinite. Pi n called, it's called pi n.
Okay. So number of primes up.
Approximate.
Sorry.
By log n.
What is approximate? Can you explain that?
It's approximate to, means asymptotically n by log n.
Asymptotically, numbers less than n. This quantity asymptotically similar to n by log n. Now, so you guys have seen this asymptotics there, right? And you guys forgot about it, or didn't want to say it in because of shyness. So this is another very useful thing, and another one place where it is very useful, that the number of prime numbers that is less than or equal to n is actually, as n tends to infinity, it becomes something like n by log n. Not something like it, it kind of tends to n by log n. This is a very another place where asymptotic notation, asymptotically similar expression is used a lot.
Sir, here the base of log is n or, sorry, 2 or e?
E. Here also it's E.
Okay.
Okay. So this is like the second base to exact equality. But now think of it that there are functions where this expression might not be even valid. So for example, I am defining this function, okay, that f of x equals to 100 for all odd numbers and 99 for all even. And g of x is 99 for all numbers, all integers. Now look at these two functions f and g, and we are only interested in the f. I mean, maybe I should have not written it n. I should have written it as natural numbers. Okay, in fact, yeah. In that case, these two numbers, you understand that these two functions are very close to each other, right?
Yes, sir.
But right, or maybe if you want to make it, this is 100n, 99n for f of n is 99n for all odd n and all even n, and this is 99n for all integers. So these two functions are growing functions, and they are basically equal in some sense. But limit of f by g does not exist. So f of n by g of n does not exist. Okay, so this is a place. Now these two functions are very similar to each other, but still we cannot use a limit to define it, that how close they are. But do you guys see why limits don't exist?
Sir, for while finding this limit, we are assuming that the functions are continuous.
Yeah, you can. Right. Yeah. So of course, I have defined the functions on the natural numbers. Okay. So you have to really talk about. We have to be careful about this continuity part also. But that also can be done. I mean, you can think of it. I mean, you can make them continuous also over the reals also.
So LH rule can be applied here.
What will be the limit? Tell me.
So I am just asking in general, if we are finding limit in this way, then can we apply LH rule to simplify?
No, we cannot. We cannot here. The limits are not well defined. Because see, f by g is sometimes one, sometimes not, sometimes something else, right? And keeps on changing from time to time.
Sir, but if Fn is if we assume them to be same, then also can we apply the LH rule or not?
Yeah, you can actually. You can think of these functions to be I mean, if you don't apply the functions on f, right? You apply the function on n, f by g, and you can think of this f to be from r plus to r plus by kind of extending this function naturally. But they're after all just functions on the natural numbers. So as a parameter of n. So think of that n to be a varying, to be a real number, a parameter, a real parameter, and you can think of the f to be a function from r plus to r plus. And using that, you can apply the rules. But there might very well be functions, okay, where f and g are same, in fact, identically same, and still the limit of f by g I mean, okay, that cannot happen, of course. But they can be very same, but limit of f by g is not present. You cannot define limit of f by g. Okay. So in such situations, what we want to say is that, okay, see, it means that, okay, that f is, we can want to say these two things in some sense. We want to say that, okay, see, it is not equal, but f is possibly less than g and f is also bigger than g. So in that respect, when we say f is bigger, or sorry, f is, what is the first one, less than g. So the corresponding value of this quantity is that, sorry, there exists a number n naught okay, and a constant c and d in the, so n naught is in the natural numbers, c and d are in the real numbers, such that for all n bigger than n naught, f of n is less than or equals to this constant times g of n plus d. Okay, so this is a kind of a something related to f, you can think of. Sorry, related to f is less than g. But we are not saying that f is less than g, meaning in the limit something happens or some kind of stuff. We are unable to define such limits like that. So in these situations, we want to kind of say that, okay, it is this expression, that you can upper bound f by g up to a constant multiplication factor and up to a constant additive factor for all the numbers, all n bigger than some particular threshold n naught. Okay, and this is what we define as f is equals to O of g. Is it clear?
Yes, sir.
Yes, sir.
Okay, good. And similarly, we can define the f is bigger than g exactly same way. And in that case, we define it as f is as a omega of g. Okay, so these are like the weaker forms of inequality you can think of. And if I have a function that is both f is less than, if I have, say, f is less than g and f is bigger than g, then what happens after that? This implies that f is equal to g.
Equal to G.
The equivalent version of this one is that, so f is O of g. Sorry, I made a mistake over here. So this should be one, right? Yeah. So f of O of g and f is omega of g. So this is, we call it f is theta of g. So if you think of theta of g is what? That I have this function f. Okay, so here the function. And here is the g function. Now the g function initially can be, I don't care how much. After some time, it kind of stays, okay? So here is this f, okay? You look at, so I can define you a kind of a border here. So this is say f, some constant times f, okay? And this is another function. This is another constant. So C1 times f and this is C2 times f. It is like the kind of a the band around f that is there. So it says that after some point of time, the g value, the function g stays within these two bands, an upper limit band and a lower limit band. Okay. So to be more precise, this is fc1 plus d1 plus C1 plus D2. Okay, so G is between these two bands, and it might keep on fluctuating for that matter. Okay, so I mean that it might very well be that here also this G function G might keep on fluctuating here like this, but that's fine. It can fluctuate within the band. So in that case, we say f is theta of G, and mathematically or precisely speaking, f is order of G and s is omega of G. They are the two things that are there. Okay. Now there are two more asymptotic notations that are used a lot. Okay, but for that, let me explain you some examples. So first of all, first of all, so say I have this f of n to be n squared plus 100 or 1000 n, and g of n to be equals to 1000 n squared plus 5. Which is bigger? Can you say the things between them?
If n is larger than both of them.
Sorry, can you repeat once again?
Sorry.
Or large enough n?
If n is larger than both of them.
What do you mean both of them? What is the relation in terms of the O? It is called a big O,
Theta.
big omega, and theta. Sorry?
Fn is theta g. Fn is theta gn.
Correct.
Fn is theta gn.
Oh, okay. Yeah. So Fn is theta gn. Exactly. Okay. Somebody asked me that what happens with this F asymptotic to G? How does this function look at in the case of graphs? Can anybody say what is this thing? How does the function look like? What does this expression, this asymptotic similar, what does it?
It will touch. Both the functions will touch each other.
Oh, for the functions will touch each other. I mean, what do you mean touch each other?
A large
I
value
will have
of n,
to
they would be
multiply the
over.
constants C1, C2.
For large value of n, it will be mostly like y equals to x graph.
No, it will not be y equals to x. I'm just drawing the functions for f and g, not f by g or something.
For the large value of n, the gap between the two function or two line will be 1.
What do you mean by gap?
Distance between the two.
No, what do you mean distance?
The distance what we can have from that
Okay, I will explain it. Okay.
The line.
This
Sorry.
C1 equals to C2 equals to 1. This is what will happen. Okay. So there is something that at so it's not exactly equal to 1, but as you go towards it, there might be this D1 and D2 that will still remain. So F and G might be off by an additive factor of constants. Okay. But as you go further away, this constant, multiplicative constant, C1 and C2, they will become 1. Okay, or rather I would say that in that case, the C1 by C2, you can think of this to be slowly and as a tends towards 1 as n goes to infinity. But D1 and D2, they can remain far apart. There are two constants that can be there. Okay. So a good example is that, so, okay, so this is something, another hint that I can say. Okay, so before I go into that hint, let me explain you one more stuff. What happened to this thing, say, if I have a new function h, which is 5nq, which is bigger or which is smaller? How can you explain in terms this kind of stuff? In using so say in the order notation.
Fn and Gn are both of Hn.
Okay, so Fn of Gn are both of them are order of Hn. By the way, if anybody is struggling to understand whatever we are doing here, some of you are asking me questions or answering my questions, and I'm taking it and going forward. But of course, if you have any doubts, not understanding, please stop me. Okay, and I will be happy to repeat. So if Fn of Gn is order of Hn, that's completely right. But see, even if I had given you this one to be 2, then also this same would have been true, right? But I have given you 3 over here. And what does it mean? It means that, see, not only they are, in some sense, this is true, but the opposite is not true in some sense, right? So h of n is not order of Fn, right? In some sense, h of n is a number that is much bigger than Fn, not by a constant factor, not by a constant multiplicative or additive factor, but by a significant amount, which changes with time. Okay, so in that respect, I would like say, if somebody comes up with a computer which says that, oh, my computer runs in time h of n, and somebody else comes up says that my computer runs in time g of n, I would like to think that h of n is horrible compared to g of n. It is not just a constant slow up or speed up. It is horrible. Okay? So for this expression, we have these other 2 expressions, which is called, where you can think of that f is very, very small to g. When do we say that? This is when limit as n tends to infinity, f of n by g of n is equals to 0. F is much, much smaller than g. For example, here you can see that, or in this example, you can see that f of n is actually, so f of n by h of n limit n tends to infinity is actually 0. Okay. And in such situation, we write f to be equals to, now this is easier to write in a paper or something like that, but this is a small o of g. Now don't be confused, there is a big O of g and there is a small o of g. These two are very distinct, different. Big O means, okay, it is less than or equal to sign. Small o is, okay, it is very, very lower than g. Okay. And the complement of this one, which is f is much, much bigger than g, the notation is f is of small omega of g. So big omega, so we have got, what all expressions have you learned? You have got asymptotically similar, you have learned big O, you have learned big omega, combine that you have got big theta, and you have the small omega's counterpart as small o, and small omega's counterpart as, big omega's counterpart as small omega. So these are the 6 asymptotic notations that are there. And in the assignments, has an assignment on asymptotic notations been given?
Yes, sir.
Yes,
Have you
sir.
guys, you have done that?
Yes, sir.
Yeah. So that is something very important, because in asymptotic notation you will come up with many times. This will come up that okay, what is the asymptotic value of this and all. And hint is that okay. First of all, if f and g are in polynomial form, something like f is equals to n to cube plus n log n plus something, or something like that. And this is for example, okay. In that case, this largest exponent determines all of it. So the largest exponent determines the asymptotic notations. Means the asymptotic behavior. So for example here, right, I could have written here anything after that. I could have written n log n. I know what all garbage I could have written here. But at the end of the day, this will matter. This will matter, not this. This is too small compared to this. See, because asymptotics means as n tends to infinity, right? And as n tends to infinity, the smaller terms will vanish or will be insignificant compared to the larger term. So this larger term, they will determine everything. Okay, so this is when f is an exponent, is a polynomial form. And the other one is if f is in exponential form, means something like 2 to the power some object or n to the power some object, then you have to make them, just 1 second, I have to take a call. I'm getting a call from the D. Hello. Yeah, so if f is in exponential form, then make them into exponent with same base. Okay, meaning make this n to be equals to 2 to the power log n or something, the same quantity, make them equal, and then compare the exponent. And this is what will happen. But in this setting, there is an issue. In this case, there is an issue. What is an issue? In the exponent, even a constant additive might be different. For example, 2 to the power n square plus 1 and 2 to the power n square. Sorry, I made a mistake over here. N to the power n square, n to the power n square plus 1 are very different objects. Why? Because this quantity is nothing but n into n to the power n square, and this is n into n to n to the power n square. So this is actually what we call a small omega of this. This one is very important in this setting. Okay. So this is the stuff about the asymptotic notations. Okay. Now I have to say a little bit more about, think that this is something possibly was covered, but many times when we try to solve, so see, you can have things like this one, like Tn equals to 2Tn over 2 plus n. log n or something like that. And you might want to say that, oh, this means that T of n equals to theta of n log square n or some kind of stuff like that. Okay. This is what we say that when you have an expression okay, I got a chat thing, but I will could answer to that maybe a bit later.
Sir,
Yeah.
sir, while checking for equivalence of two functions,
Mhm.
can we take log of both sides?
No, that will not be useful necessarily. I mean,
Sir,
that is you
useful,
can log
but
of both sides, and but then you have to look at. I mean, you can take a log of both sides. Actually, that's true.
sir, because sometimes it gives wrong result. It makes them equivalent, but they are not actually equivalent. Like in this case, n की power n square plus 1 and
Exactly. So
n
when you
power.
take a log of both sides, then you cannot just worry. Then you have to look at everything. Then you have to, after taking log, you have to take care of even the constants.
Then we cannot apply that limit.
No, then you
formula.
cannot apply the limit. No.
Okay, sir.
If you take log, after that you cannot apply limit.
Yes.
Okay. So before I go into, so someone pointed out something about here. Which is the one that you told? This one. I think Luna Bishas asked a question about for the log expression. Oh, why are they equal? Okay, I will not. Okay, go and think about it. Okay, so why this implies this? Okay, the opposite is not true. The opposite is not true. Meaning, if I have log and equivalence in the log, then that doesn't mean that it is equivalent in this original one. But this direction is true. Okay, so what I meant was that if f of x, yeah, I mean, yeah, go and just do it yourself and you will understand. This f is asymptotically similar to g, then log of f is also asymptotically similar to log of g. So yeah, coming back to whatever I want to say, and I want to stop in another 10 minutes because I have a meeting after that. Okay, so if I give you an expression like this and you can give me a expression like this, that's perfectly fine. Okay, this is something that possibly was done and we will do it further or more of it soon enough. But there are the other times when I can ask you something, I can give you like this: Tn equals to 2Tn over 2 plus order n. What does this mean? What does this expression mean? If I ask you to, if I give you this expression and ask you to solve for Tn, how will you solve it? Has this thing been covered in your class till now in this by the TS?
No, sir.
No. How? What does this expression mean? Say I tell you this thing. Okay, so this is a merge sort kind of stuff. That T of n equals to 2Tn over 2 plus order n. What is T of n? Can you give me an asymptotic value of T of n?
Of n log n.
This is n log n?
N log n.
Okay, but let me give you a quick answer. Okay, so let me prove it by induction.
Tn should be less than equals to n log n.
By induction, my induction hypothesis is that T of n is order of n. Okay, so why? So I have to give you the inductive step. Okay, so of course there is this, we assume that So we know it for all n lower than something. So T of n is equal to 2t n over 2 plus order n. Now this is equal to 2 times order n over 2 plus order n. This is by induction hypothesis. Now 2 times order n over 2 is also order n, and this is also order n. 2 orders, how does it matter? It's like order n. Right? So T of n equals to order n. Right? Fine. Any questions about this?
Can we apply induction on asymptotics?
Yeah. This is something, this is a false proof, of course. Okay. You know that this one means should give you T of n equals to n log n. So this is, of course, wrong. Okay, this is wrong. The reason it's wrong is that whenever this expression is given, you should not take it as face value. This is a, you can think of it as a particular, this is a kind of a shorthand for a particular expression. Okay, so this is actually a shorthand for, that means there exists some constant. Okay, I don't know what is that constant, C and D, such that T of n equals to T n over 2 plus C times n plus T. This equation is the original equation. This is the shorthand for that. When you apply induction, you should apply the induction on this, not on this. Okay, if you apply induction on this, then you will get garbage like this. But if you try to apply the induction on here, then you will realize that, okay, what happens after that. So this is a very crucial thing that is there. Okay, if I give you a recurrence relation using asymptotics, then you should first convert it to a proper recurrence relation and then apply induction hypothesis, not before that. Is this idea clear?
Yes, sir.
Okay, you can see that there are, I mean, you can fall into serious pitfalls because of this if you don't apply accordingly. Okay, so okay, so now good. So
Sir?
yeah.
So if we have little o of n instead of big O of n in our recurrence.
Yes. Yeah. So, if
So
you have a little
like
of
in
n,
that case,
if you have a little of n also, okay, then the best way of thinking of it is that you can think of it as n by some by k, where k is something that is more than a constant, and continue with that. Okay.
so could you repeat once more?
If you have a little o of n, so if I have something like T of n equals to T of n over 2 plus little o of n, then this I would do it in this way, that okay, this means that T of n equals to T n over 2 plus n by some k, where k is a function in some sense, phi is a parameter bigger than 1, bigger than any constant, and then try to solve this expression. Okay, then this expression will be an expression in terms of k. Okay, and then we have to see about what happens there. For example, this expression, if you do it like this, then this will actually end up becoming yeah, so actually small o of n is a bit of complicated thing to do, I must say. It is not the most easiest thing to do actually. Okay. This is not an easy thing to do. Yeah. Yeah, so the other option to do is actually to leave it with, to have it with order of n. You solve it with order of n. Okay. And you get some order. So that is one thing that you can do. But you have to, yeah, you can with some proper working around with it, you can think of it to be as whatever this expression is, right? So if you work with this one, then you will get t of n equals to n log n. Okay, but since this one is the order of n, we have relaxed small o of n to big O of n. So the actual expression for this one would be t of n equals to small o of n log n. Now, yeah, so with small o, there is no particular standard way of getting down to it, around of it. You have to be a bit careful over this one. I mean, this is an easier one. There are other things where things can get even more trickier.
Sir, I have two doubts.
Sorry?
Sir, I want to ask something.
Yeah, go ahead.
So one thing is that can we use Master's theorem for this type of questions?
You can. Okay. Now the reason I kind of avoid master theorem is that master theorems is kind of a, first of all, I don't like any theorems to be memorized. Okay. So there is a concept of master theorem. Okay. And you guys can find this statement in many books, in both in algorithms and in various notes and all. I will not be proving that master theorem. Okay. The reason is that first of all, master theorem requires some more amount of, if I tell you, oh, here is the master theorem, you will end up trying to memorize it. But that is completely useless because you will memorize it for the discrete math course, but then you will forget for the algorithms course. And that will be completely not good for me. Secondly, it is easy to prove. First, it is pretty easy to prove. So I would like you guys to go and take a look at the master theorem and try to prove it yourself. And you will see that it is just a small induction that you do. There are 4 or 5 cases, and in each case you apply an induction. So you, for any theorem at this, I mean the kind of work that we do, okay, it is important to know the technique, how to solve it. But memorizing something is not at all useful. Okay, because you don't learn something in ISI to just get a good grade. I mean, the attempt is to kind of explain you things so that it kind of goes deep into you. Memorizing is not the way to do it. So instead, try to prove master theorem by yourself, and you realize that there are very trivial things to prove. So if at all you need master theorem at some point of time, you will just in 5 minutes prove it yourself. And second problem with master theorem is that it just handles just 4 cases. Okay. And what happens other than the 4 cases? No, it doesn't do anything. So if the recurrence is not of this very standard form, then you will not be able to understand or get, be able to apply this master theorem. Master theorem sounds like some kind of theorem that you can apply everywhere, but that is not the case. So I don't prove or even state the master theorem in the class usually. Okay. So master theorem, I know, there exists this master theorem, and I would encourage you guys to go and take a look at it to kind of convince yourself that, oh, that's an easy theorem to prove. Okay. And yeah.
And so one more thing, it is if something is smaller of something, suppose if n is smaller of gn, then it is also bigger of gn also, right?
Yes.
So
yes.
if it is not mentioned, then can we leave it with big O?
You can leave it with big O. So big O, you will get some expression. With small o, you can get something tighter. These are all inequalities, right? Tighter inequality is better. So if you leave it with big O, then that will give you some nice results. So here, for example, you can get to here, and this is a valid thing, completely correct thing. But what I told here is that there might be ways to get something even tighter result, even better result. But this is completely correct. Okay. So there will be times when I will be giving you some kind of recurrence relations. Okay, so Tn equals to something, 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 say 2Tn plus 4 log n over 2, kind of some stuff like that. Now, usually, this is how you should try to solve it, and I will say that over solve for Tn. Okay, if you can come up with an equal thing, exact expression, great, that's wonderful. If you cannot, try for asymptotics. If you cannot, try to see can you prove less than or equal to. If you cannot prove this one, try to prove order. If you cannot prove it, then try to see whether you can prove a lower bound thing. And if that is also not coming up, then try for omega. And if of course both of them comes up, you get theta. Okay, so this is how you should be doing it. And if you have this one but not this one, then try to solve for small o and small omega. So this is like a kind of not very well specified problem. I will give you problems like this, that I will give you a recurrence relation and say solve for Tn. And what I expect you to is to think about it yourself and try to see what you can do. So it might happen that someone has proved this one but not this one. Fine, that person will lose a little bit of marks, but so be it. Somebody might have been able to prove theta, but somebody else has managed to prove asymptotic case. The person who has proved asymptotics will get some marks more than the others. Okay, so these are kind of these vague things which you have to understand it on the fly. Okay, it is exactly like inequalities. When somebody asks you to solve an inequality, there is no, you can solve somebody can give you an inequality. Somebody else can come up and give you an even tighter inequality, right? And both of the inequalities are correct. Just that one has given a bit tighter inequality than the other. And so that person might get some more marks. But I leave it like this mostly because this is how we do research. In research, we don't have anybody saying that what to do. I have a recurrence relation and I expect it to be solved in some way. Yeah. Any questions? Any other questions? Comments? Okay, so if not, then I think what I will do is that I will make a quick poll about understanding how many of you are MTech students and how many of you are PhD students. And after that, I will just stop the class for today. What is the difference between less than and order? So less than is So ordered is this asymptotic stuff, right? It's for every x, f of x is less than g of x. This is better than saying for the higher terms, fn is less than a constant times gn. Okay, good. So I got some ideas about this thing. So okay, so thanks. I will possibly try to take one more extra class, before Friday, but I will let you know when.
Sir, actually after this class, I understand there was some mistake in assignment because we did not have much concept.
Okay.
So
Can you just point it out to me? I mean, maybe send a mail or something like that, and then I can take a look at it.
No.
Oh,
I
you
have
have mistake in the solutions.
Yes. I did not have much concept, so I did some mistake in
Okay, so
solution.
if you want to, I have not checked that assignment. So if you want to resubmit it, you feel free to resubmit it.
Okay, sir. Thank you.
Okay. Okay, chalo.
Sir, in the big O notation,
Yeah.
Can we remove the D term also plus D? Because
technically you can actually. You're right. Technically you can. In the big O notation, technically you can remove the D term.
Okay.
Sir, if we remove the D term, then how will the graphs for this asymptotically similar look like?
I mean, in that case, you have to put the D back.
Oh, okay.
I mean, in the graph, you will have to have it put back.
Oh, okay.
Yeah.
Sir, for the theta, can we have the similar kind of thing? I mean, removing D.
You can also do the similar kind of thing. See, mainly because there is this, I mean, for all large enough n, right? So choose that n to be some massive number. I mean, you can with some certain small caveats. Okay, so f has to be bigger than 1 at least, and so on. Okay, as n goes to infinity, f should be bigger than 1. Only then you can remove d. Okay, the function will be bigger than 1 or bigger than a constant. So if the function goes to 0, then you cannot remove d.
Okay.
Okay, so there are some caveats that are there, but I don't think you guys will face those kind of caveats, at least not in your MTech course.
Sir, hello.
Yeah.
Sir, how will you solve the Tn in terms of the tilde symbol?
How will you solve what?
Solve Tn, I mean the recurrence relation
In terms of the tilde symbol? That's a good point. It's not easy. So one way is actually to compute the actual value of, or close to an actual value of Tn, upper and lower bound or some kind of stuff like that, and prove it for the asymptote with the limits and all.
But sir, that will be say this.
Or the other way is actually when you do this theta, right? The order and omega. The order and omega in the polynomial term you get something, but the constants in the for the largest term is 1. So one of them is O of n square plus 500 something, and omega of of n square plus say or minus 300 something n. Okay, since the largest exponent is n square, and their coefficient is 1. So from that you can guess that T of n would be asymptotically similar to n square. Okay.
Okay, sir.
Yeah.
Sir, monotonically increasing or decreasing will affect the asymptotic.
No, not monotonically increasing decreasing will not affect the asymptotic as such. No, that will not be the issue. Okay. Yeah.
Sir, how can we handle the floor or ceiling value in the recurrence relation?
It is very hard. So that's why we have to go for the order notation, therefore. Okay. Floor and ceiling values are kind of very ugly to, very messy to handle.
Sir, can you like show us like not like if it's not possible today, then also okay. And even in the next class also, if you can like illustrate an example on how to solve this floor and like recurrences with floor and
Okay,
ceiling.
sure. I will do that. I will do it in next class. I will show it.
Like specifically in the assignment, there was one question where we had the ceiling of like log n.
Okay.
So
I mean, based on the ceiling of log n, just replace it with log n plus 1.
okay.
Upper bound, right? And then you can live with that.
Oh. Okay.
Right. And then you have a expression. Don't try it for, once you have this floor and ceiling and all, trying to get an exact expression is not a very good idea. Hello?
Hello?
Yeah. Can you hear me?
Yes, sir, you're audible.
Yeah. So when you have floor and ceiling, then I would never go for an exact expression. Okay. Since I will anyway go for an order or theta or something like that. So losing one additive factor of 1 or some kind of stuff here and there should not matter. There are times when it might matter, but then you have to kind of replace it with bit carefully.
Okay. Actually, I was trying to solve that by that method of substitution, but I got like messed up at the big in the middle of some after few number of steps. So
Okay, I will take I will try to go over one at least, but again, all of them are different styles, so there's no particular same thing. But I will go over one example at least.
Okay, sir.
Okay. Any other questions? So if not, let me go. I have to rush to the new terms. Okay, I'll see you later.